Hi class, here we are again on a snow day, and we're going to cover the material anyway just because we've got it all planned out, and it's not too terribly painful, I hope, watching these videos. Alright, I want to talk about regular grammars today. We talked a little bit in class the other day about grammars in general, but today I want to talk about a special kind of grammar called a regular grammar. That's what our worksheet is about, and I attached the worksheet to an email to you, or I will. Let me show you what a regular grammar looks like. You still have a starting non-terminal, excuse me, or a starting variable, and it has rules just like in other kinds of grammars, but the rules, right-hand sides, the things that you replace the variable with, they have a certain shape. The shape for regular grammar's rules are either a non-terminal or variable gets replaced by a word, something made completely of terminals like ABA or BB or even lambda, something that is a word, or if it has a variable in it, if this right-hand side of the rule has a variable in it, then that variable has to be at the very end of the replacement substring, and there can only be one. So you could say something like AS or BBAT, something like that. Those are the shapes of the rules for a regular grammar. So either it's a word, like all these are, or it's something that we call a semi-word. So it's a word followed by exactly one variable. The variable has to be at the far right of the rule, and there can only be one. So this thing, only one, and it's the last symbol. And all the rules in the whole grammar have to have that shape in order for it to be called something, well, okay, let me not tell you fib. A grammar that looks like this, where you've got words and semi-words where if there is a variable, it's the very last thing, that's a kind of grammar called a right linear grammar. Right linear. That is one type of regular grammar. It's the only type of regular grammar that we're going to play with. If you had a left linear grammar, what would change is that the grammar's rules would either be all words like these, or they would be semi-words except the variable would be the leftmost symbol instead of the rightmost symbol. Those are regular grammars too, but we're not going to use those. We're just going to call right linear grammars, things that look like this, those are going to be our regular grammars. But keep in mind, and the author tells you in the book, that left linear grammars are regular grammars too. Now, one caveat. It has to apply, if you're looking for a regular grammar, then you pick either right linear or left linear, and you make sure that every rule in the entire grammar is the one that you picked. So they all have to be right linear, or they all have to be left linear. You can't have some rules be right linear and some rules be left linear and have a regular grammar. That doesn't work. Okay, now what's special about a regular grammar is this. No, I don't want to save changes. Hold on. I just want a clean slate. If a grammar is regular, then it generates a regular language. No, not writing very well. That's supposed to be an N right there. It generates a regular language. What's a regular language? It's a language for which you can make a finite state machine or for which you can make a regular expression. So if you have a grammar that is regular, you know that you can also have a machine for that language, a finite state machine for that language. You can also have a regular expression for that language. Okay. If a grammar is not regular, it's one of those kind of grammars we were looking at the other day, some of which might have been regular. I wasn't paying attention at the time. But if you've got a grammar that is not regular, that does not mean that the language it generates is not regular. It might be regular. It might be that there's a regular grammar for that language. It's just that the one you're working with is not a regular grammar. So if it's not a regular grammar, you have to play with the language a little bit more to decide whether or not it is regular. Let me finish this sentence. That does not mean that its language is not regular. All right, now I'd like you to look at your worksheet for today. There's an algorithm at the beginning of it that is going to tell us how to take a grammar that's a regular grammar. As a matter of fact, it's a right linear grammar. Those are the only kind we're going to use for our regular grammars. How to take such a grammar and turn it into an equivalent machine. First thing you do is draw a state for every variable in the grammar. You make the state for the starting variable, which is usually called S but might not be your start state. And then you draw one extra state and make it be an except state. And you call it something like F for final, or if you don't have an A, you can call it A for except, but call it whatever you want, just as long as there's not a variable by that name already. Then you go through, and for every rule in your grammar, the rules, by the way, are also called productions. I didn't tell you that the other day, but a rule and a production is the same thing. So for every one of these rules, you make an arrow from state X to state Y. These are for the semi-word rules. And you label that arrow with W. Now, W might have more than one letter in it. That's okay. You can split the states up or add some states, split that label up later. If X and Y are the same variable, then you just make a self loop. We're going to do examples, so you'll see more about this. If you have a rule that is just a word on the right-hand side, then you draw a transition from X to that except state, that single except state that you made, and you label it with that W. That could be lambda, by the way, this word. I'm just using W for a variable. W is not a character in our alphabet. W is a variable that holds a string made out of the letters from our alphabet. And then you can bust up your states according to the way we did when we took a machine and turned it into, no, when we took it, this is wrong. I got to correct my handout. When we took a regular expression and we made it into a machine, that's what that should have said. Okay, I'll fix the handout before I email it to you. Now, let me do an example. There is an example on your worksheet. So you can look at that example. Let me just make a little copy of it here. Here are the rules for that grammar. Okay, this example is in your worksheet. It's the first one. Let's draw this together. Now I want you, in order to get the points for today, to actually either write this on a piece of paper, plain old piece of paper is fine, or if you want to print out your attachment of the worksheet and write on that, that's fine too. Whatever you'd like is fine. So let's do this example right here. The algorithm said we make a state for every one of these variables. So let's make ourselves some states. Here's a state for S. Here's a state, and I don't know exactly how to label these, or to lay these things out so they look pretty, but if I look up here, I see that I'm going to have a transition from S to X labeled A. So let me just put that in right here. Here's X, and this is going to be an A, because that's the way you do these rules. You have a state for this variable Y. You also have a state for this variable Z. And if I'm looking at S's rules, I see that S has a rule BZ. So I'm going to put Z right here where it's conveniently located for this transition that it has from S labeled B. So you draw a state for every variable. This is your starting state. So let me put this little arrow here. And then for every rule, you make a transition. And the way you do it is make an arrow, a transition from this state to this state, and you label it with this word. Make another one from this state to this state, and you label it with this word. Now I need a state Y. Who goes to Y? Let's see, X has a transition to Y, so I'll put Y right here. I also need an except state F. I don't know exactly where to put it. This is going to go to F. That's a word. This is going to go to F. So I need access to F from S and from Y. I don't really have a good place to put F. Could stick it right here in the middle. Why don't I do that? Put that state F. You always need an except state in your machine that the words go to, the words that are the rules that are words. So S has a transition that's a whole word, lambda, so I could take a transition to F that way. Now let's do X's transitions. X has a transition to S labeled A. So we put this in. X has a transition to Y labeled B. So here's this one. Y has a transition to X labeled B. And a transition to Z labeled A. And it also has a word rule, so that goes to this except state, and it is lambda. Now we have to do Z. Z's rules, one goes to Y and it's labeled A, and one goes to S and it's labeled B. All right, now the worksheet asks us to look at this and figure out what machine this is. What language is that grammar generating? Oh, you know, I think I see. This, if you instead of having these transitions that are lambda going to F, you could have an except state here and an except state here, because anytime you're here you can just slide over and accept, right? So these two things could be except states themselves. And if we had that, then we would have that parity of two letters machine. It's very symmetric. There's the A's, the B's, the A's, the B's, four states. These two are the accepts. That means this one, remember, is even and even A's and even B's. And remember, this one is odd A's and odd B's, odd state. And so that's what this grammar generates, and that's what this machine accepts. It's the strings that have either an even number of A's and an even number of B's, or they have an odd number of A's and an odd number of B's. So the parity of A's is the same as the parity of B's. That's what that grammar is doing. Now the next thing that the worksheet tells us to do is to make a new grammar, except to make one for strings where the parity of the A's is different from the parity of the B's. So, which states need to be our accept states? This state and this state. Those are the ones for even, odd, odd, even. Now, what do we do in this grammar to make that change? Well, instead of this rule that goes to F from S and this one from Y, we need to have transitions that go from X and Z to the accept state on lambda. And so what's going to change in this grammar, this is going to go away, this is going to go away, and we're going to add a rule to X or lambda, and we're going to add a rule to Z or lambda. Then our machine would have these two states being accept states rather than those two states. The next example on your worksheet is this one. I don't want to do the whole thing because you need to practice this algorithm without me stepping you through it. You don't learn as much if I hold your hand through the whole thing. So let me just get you started. You want to draw your states. Begin with S. Each one of these will have its own state, and there will be a state F, the accept state. You can kind of lay your machine out as you go. You've got two S rules. One goes to X and one goes to Y. And so draw you an arrow to X. Draw you another arrow to Y. And label the one to X with an A. Label the one to Y with a B. Then keep going. X has two transitions. Y has two transitions. Z has three. So Z is acting Z is going to be like an accept state because it's got this lambda transition that's going to go to your F or your accept state. So finish drawing the machine, and then to answer this question, look at that machine. It's going to be one of those substring machines that has two backbones. Here's the beginning of a backbone for a string that starts with A, a substring for A, and here's one for a substring that starts with B. To answer this question, just look at it and tell me which two substrings is this machine looking for. The next example is right here. It's another right linear grammar, but it is a little different because we have longer word things here in our semi-words, word beginnings, and we have a longer word there and a longer word there, and we don't have any lambdas, so this one's going to be a little bit different. Let's try it. We have a state S, that's our start state. On this substring ABA, we need a transition that goes to X. So here's X and ABA goes there. Now, isn't this looking like one of those partly finished machines that we got when we were doing that turn a regular expression into a machine algorithm? It looks just like that. The other transition for S goes to Y, and it is labeled AABB. Now, X has one transition that's a word with no variable at the end, so we're going to need to take it to the accept state. Here's our accept state out here with my jiggly lines. We'll call it F because that's what the author does. And this transition that goes there is labeled ABA, same as that one. Now X has another transition that goes back to X, labeled B. Okay, let's do Y now. Y has two transitions that both go to F. That's a mistake. That was supposed to have a Y right here. I need to fix my handout. Okay, I fixed your handout, so it'll be correct on your handout. This transition, AY, means we need a transition from Y to Y, labeled A. We need another transition from Y to this accept state out here, labeled BB, AA. All right. Now, if we wanted to finish the machine and turn it into a deterministic or non-deterministic finite state machine, you're not supposed to have more than one character on a transition. And so what we would have to do is break this apart over concatenation and add an intermediate state and put A on that little piece, and then add another intermediate state and put B on that little piece, and then put that A on that little piece. So we'd have two more little intermediate states over here, and we'd have three little intermediate states here and here if we wanted to do that. So we could, but it says here, you may leave the machine as it is this time because we just want a rough visual representation of what a machine for this grammar's language would look like. This gives us a picture, at least for me, that this doesn't give us. Grammars, I don't know, they just don't jump in my head so easily as a picture. I can see what the language is that this machine will accept much more easily from this picture than I can from this grammar. But that's me. I'm very visual. Now this next part says, look at your machine and write a regular expression that generates that same language. A regular expression, huh? Okay. Well, you've got two ways to go from your start state to your accept state. And you're not allowed any more letters once you get here, by the way. There's no loop on A or B here. State F is a final state in the truest sense when you use this algorithm. So you've got this way to get to the accept state, or you've got this way to get to the accept state. So what do you think that regular expression is going to look like? I'm going to do the top part. You do the bottom part. So the top part says you have to have an ABA. Then you can have 0 or more B's, so that's a B star. Then you can have ABA. Then you need an OR, and then you would do this bottom part and put it right there. Now we have one more algorithm to learn today, and that is to go in the other direction, to start with the machine and turn it into a right linear grammar. That's what this RLG here stands for, right linear grammar. And remember, that's the kind of regular grammar that we are looking at. So here's the steps of this algorithm. First of all, you look at your machine and you name your states capital letter names. And typically you'll make this one be an S, just because that's our convention with grammar. So these states are going to turn into variables in your grammar. So you want to label that one an S typically, and then pick other capital letters and name your states by those capital letters. And then you just kind of go backward, and you would make transitions for you. Like if you call that S and you call that T, then you'd have a transition in your grammar that says S can be replaced by AT. So let's do this now. Oh, and here's one important thing. If a state like this one is an accept state, then you give it a lambda transition. You just make a lambda for it. Remember how we used to go to a state F on that? Well, we don't have a state F in our machine, so we just give that this very state right here, a lambda transition, and it serves the same purpose. And then when you write your grammar, you always do your start states rules first. So let's see. What if we do this one? Let's call this guy S. Let's call this one T. And let's make this be U. I hate to do U and V because they look so much alike. Let's call this guy X. All right, now my grammar is going to start with the S rules. And then I look at its transitions. It has an A that goes to T, so I'll write that one. It also has a B that goes back to S, so I need to add OR BS. And S is not an accept state, so I don't have OR lambda. Now let's do T. T has a rule, or excuse me, a transition on A that goes back to T, and it has a transition for B that goes to U, B, U. And it's not an accept state. U has a transition on A that goes to T. It has a transition on B that goes to X, and it is not an accept state. X has transition for A that goes back to X. You got to separate them now. You can't put a comma here. It has a transition for B that goes back to X, and because it's an accept state, we add or lambda. And that's our grammar. Now, this last question says, what language does that machine accept? Well, take my advice. Look at the picture. Don't look at this because this is harder to figure out. Look at the picture. It's a substring machine. It's got its little substring on its backbone. So tell me here, maybe you should write a regular expression for it just for practice. What language does that machine accept? All right, I'm sure that you knew when you looked at that machine that it was accepting strings that had an ABB in them. The next part of the worksheet points out that that grammar that you wrote, that you made from that machine, that's not the only grammar that will generate the language of strings that contain ABB. As a matter of fact, look at this grammar right here. This is not a regular grammar. Can you see why? Look at its rules. This rule right here violates the property of a right linear grammar. It has two variables on its right-hand side, and it's only allowed to have one if it's going to be right linear. And so if we took off that X right there, then it would be a right linear grammar. However, it wouldn't generate the same language. So this is not a regular grammar, but we can still figure out what it does fairly easily. Look at the S rule. There's only one S rule. It makes something that whatever X makes, it makes one right there, and then it puts an ABB into the string, and then it makes another X thing out there. Well, what kind of things does X make? If you play with X and make some strings, you'll see that you start with X and then you replace it with one of its rules. If you pick AX, you'll get a working string of AX. If you then replace this X with BX, you'll have that A, and then you'll have BX. And so if you keep going, you can see that X makes any string that you want to make out of A's and B's. If you replace this X with lambda now, you just get the string AB. X is one of those X has rules that can make any string at all out of A's and B's. So if you think about it, this is an A or B star, followed by ABB, followed by A or B star. And that it's making the exact same language that the grammar you made from the machine made. So it is doing the same thing, and that language is regular, isn't it? You made a regular expression for it. You started with a machine for it. The language is regular, but this is not a regular grammar. So you can make a regular grammar for any regular language, but you can also make non-regular grammars for regular languages. Now, this is an important thing here. We wrote it earlier on. It says, if a grammar is a regular grammar, then it generates a regular language. However, non-regular grammars can generate regular languages, so just because a grammar is non-regular does not mean that the language it generates is non-regular. Okay, this is the last part of our worksheet for today. This is a machine for you to practice on. What you want to do is label your states with capital letters, whatever letters you wish. Write down the rules of the grammar. And then just for practice, look at this machine, figure out what it's doing, and write a regular expression that does the same thing. Now don't trouble yourself with running that NFA to Rex algorithm. That thing is a pain. You can figure out how to write this regular expression just by studying the machine. If you see what it does, the regular expression will come to you. This top part, once you get up here, you can't go down here. And once you get down here, you can't go up there. So strings that start with A stay up here, and strings that start with B stay down here. And there's something special about these, the way these states are configured. Strings that start with A have to do a certain thing in order to get here where they get accepted, and strings that start with B have to do a certain thing to get here before they can be accepted. So you think about that, and then you turn that into a regular expression and write it here. And then one last thing. We know now 3 different devices that we can make for a regular language. We can make a finite state machine, we can make a regular grammar, we can make a regular expression. I know which one helps me see what's going on the most clearly, the most easily, and that's the picture. But I'd like you to think about it. Which one helps you the most? And as the problem gets larger, suppose you have a language that's really complicated. As the problem gets larger, does your answer stay the same? Probably for me it would, because the visual aspects of that picture help me so much more. But in some cases it's possible that one of the other 2 might help me more. It's just kind of hard to say. But I want you to think about that and jot down your answer here. And that's the end of our worksheet for today.